here we go. So we're going to play around with a low Earth orbit. And low Earth orbits are orbits that have, the satellite has an elevation of somewhere between, I think it's 160 kilometers, and I think it goes up to 4,000 kilometers on average from Earth. Example, the International Space Station has an average radius of about 400 kilometers from the surface of the Earth. The Earth has a radius of approximately 6,360 kilometers. So let's suppose that there's a little deviation. We know orbiting bodies orbit not in a circular, but in an elliptical pattern. So let's say that for the International Space Station, there's a minimum distance elevation of, let's go with 400 kilometers, and a maximum elevation of 500 kilometers. Now, really, for our orbit, we're orbiting around the center of mass of the Earth. So let's suppose that is in the center of the Earth. So our min is actually 400 plus the radius, 6,360 kilometers, or 500 plus 6,360 kilometers. So what we want to do is, based on the center of the Earth, we want to come up with the path of this object. So then our minimum distance from the center of rotation is going to be 6,760 kilometers minimal and 6,860 kilometers maximum. And I was calling these guys little m and big M in my notes earlier, because I kind of want to track what happens to them. Now think about a polar ellipse. Polar ellipse is going to have a formula something like r equals some number k divided by 1, and it could be a plus or a minus and a sine or a cosine. I'm going to go with a plus, the eccentricity of the orbit times the cosine of the angle. So what we want to do is given this information, can we come up with k? That ends up being what we call the length of the lattice rectum. So just a sketch of this situation. Let's suppose here's my orbit. The focus is going to be right around here that we're orbiting around. The distance of this radius over there, that's my 6,760. And we can say that happens when theta is 0. And then over here on the other side is my 6,860. And that's going to happen when theta is what? Pi. Yeah, that's going to happen when theta is pi. Now this is really stretched out because this is such a tight orbit and there's such a minimal distance, right? 100 is the distance between them. This really looks pretty damn circular. So my image here is very distorted. So just keep that in mind. What I can then do is take that information over to this equation here, because if theta is 0, cosine of 0 is 1, right? So we get that smaller radius there, the 6,760, that's my little m. That's equal to k over 1 plus e. And then we'll get on the other side our 6,860. That's the number I'm considering to be my capital M. That's going to be k over, what's cosine of pi? -1, right? So that's going to be a 1 minus e in the denominator. And that cleans up kind of nice, okay? So if we tweak these guys, like solve for k, the bottom one tells us that k is equal to that maximum number, sorry, the 6,860 times 1 minus e, but the one above tells me that k is also equal to the min 6760 times 1 plus e. That's kind of nice. And again, I was calling these also, that's my little m there and my big M there. And if you whip out some algebra, so we can clearly set these equal to each other, right? Because they're both k, and we can solve for e there. And so what happens when we do that is we find that e is going to be equal to big M minus little m divided by big M plus little m. And so for us, for this situation right here, our E is going to be the difference between them is 100. And the sum of the two of them ends up being, let's see, what is it? 0, 2, 6, 13,620. So this ratio right here is our eccentricity for this orbit. And that reduces a little bit. If we wanted to write it as a decimal, it's sort of like I calculated earlier, it's like 0.007-ish. Oops, come on, pen. So that's approximately 0.007. If we reduce it, let's see, that would be 10 over 1362. Cut those in half. We're going to get 5 over, see, 2 goes into 13, what, 6 times? 16 8 times, and 2 once. So I think 5 over 681 is as small as we could get it. So that's our E right there, either as a approximation of a decimal or as a fraction there. And then we can back substitute in here to calculate K. So I was just, and you could check this later if you want, I was messing around algebraically to see what K is going to look like, and I found K is equal to 2 big M times little m divided by big M plus little m. Otherwise, we know that it's that little m times 1 plus e, right? So for us, that's kind of a more complicated formula, but I thought it was kind of cool that k can be expressed just in terms of the min and the max in this cute little fraction. But more convenient is just to say it's that minimum 6,760 times 1 plus that reduced fraction 5 over 681. And so what does that come out to be if we approximate it? Let's say I wrote that down somewhere. Where did I write that down? Did I lose that sheet of my notes? Oh, this is it, maybe. 6,810-ish, if we round to the nearest whole number. Anyone else get that? Yeah, okay. So that'd be approximately, if I go to the nearest whole number, 6,810 kilometers. That would be kilometers, right? Yeah, kilometers. No, it's unitless. Wait. No, it's kilometers. Yeah, it's kilometers. Yep. Sorry. Okay, so now we have an equation. We have that the path of our International Space Station is approximately 6,810 divided by 1 plus, and then if I use I might as well use the decimal since we already rounded that, 0.007 cosine of theta. And remember that if E is 0, what shape do we get? We get a circle. So this is pretty damn circular, yeah, if we graph it. So let's have Desmos graph it for us, and then we'll take a look at the major axis and where the other focus lives, which is kind of neat. So Desmos, and we've got R equals 6,810-ish divided by 1 plus 0.007 times the cosine of theta. And then I'm gonna have to zoom way out to see this sucker. see, this way, right? Yeah. Into the thousands. And we could have scaled it down by dividing k by 1,000, and then we'd have a graph where each number's in thousands, which would probably be a better idea, but that's okay. So this is my graph. It looks pretty darn circular. Okay, so just some other things I want to take a look at. I'm going to plot the points, and I can't do, again, one flaw in Desmos is I can't do polar points, but I should have pretty darn close the point 6,760, 0 should be that closest point on the right, and the furthest point on the left for x would be a negative 6,860, 0. Because we rounded these two numbers here, if we zoom in, we'll see the point's not quite in the right spot, but if we didn't round, we would get it in the right spot. But then otherwise, we would have crazy fractions everywhere, which isn't too bad. Some things to consider graphically. So we're orbiting the pole here, and just to see how tight this orbit is, if we looked way out and was watching the International Space Station orbit from like some spaceship, some aliens are watching that happen, what would it look like to them? So the Earth's center of mass is we're assuming it's the origin, and let's say the Earth is a perfect circle, then its equation would be r equals, what was it, 6,360 for the radius. Okay, so we have a pretty tight orbit. So the Earth is everything inside this orange circle is the Earth, and the International Space Station is hugging pretty tight around there. Okay. It's a little farther away over there than over here. This is the closest, that's the farthest away it's going to be. Okay, so it's progressively getting slightly farther away as we rotate this way, and then this way it's progressively getting closer to the Earth again, but not by much. Okay, so some other things to think about here. So we've got our orbit. It looks something like this, pretty darn circular. Oops, that's my circle. We have these 2 points right there. The center is going to be somewhere over here, just to the left of that focus. And so the distance from the center to the edge, remember that's the value we call A, right? So what I know from this picture then is twice A should be equal to the distance all the way across, which is my minimum distance plus my maximum distance, right? So that's my big M plus my little m. So A must be that over 2. So if we take, for our example right here, when I added up big M and little m, I got what, 13,620, was that it? 13,620. If I cut that in half, then I'm going to get 6,810 is the distance from here to here. And let's see, what else did I want to know about that? There was something else I thought was interesting. Oh, the position of the other focus. So another relationship I know is that E is equal to C over A. I mentioned that one the other day, where C is the distance from the center to the focus, and A is that semi-major axis there. So that also tells me that C is equal to EA. My E as a fraction was 5 over 681. A here is 6,810. Now that cleans up rather nice, doesn't it? It's 100. No, it's 50, sorry. There we go. Now that's the distance from the center to the focus. How far apart are the foci? they would be 100. 2c would be the distance between the two foci due to our symmetry. So just to note that 2c is equal to 100, and 100 happens to be big M minus little m, which is kind of cool. So let's just plot that just to get a little perspective on this circle here. I know that one of my foci is at 0, 0. And I know the other one now is going to be to the left of that, 100 apart. So it's got to be at negative 100, comma 0. And those guys, I mean, from the perspective of an alien looking at it, it's way inside the Earth, right next to the actual center of mass of the Earth, right? So the more eccentric the orbit is, those two spread out more. So it is possible to have an orbit for which the other focus is outside of the Earth, which it is what it is. That's just what it comes out to. But this, again, is pretty tight. So that's that. I don't think I have anything else to say about it. We could calculate the rectangular, but the rectangular version isn't, I don't know, as exciting. Why? Rectangular is good for shifting left, right, up, and down. Polar is good for what? What does R depend on? An angle. So polar is good for things involving angle, like rotations. So if we need to do some kind of rotational thing with the problem, we should be in polar. If we need to shift left, right, up, down, perpendicular motion, then it's better to have rectangular. And so usually for this kind of thing, we're more concerned about rotations, and so polar is really the better way to go for a problem like this. All right, so a brief note on, and I still haven't solved this problem completely to my satisfaction, but I'll show you what I have so far. I mentioned the other day, like, why does something have a more eccentric orbit or a less eccentric orbit? And it seems that three things are important. So eccentricity of orbits. So important things are initial velocity. So usually we call that v sub 0. So we have to have the velocity at some moment, okay? And whatever moment we decide to look at. Other things that are important are also the distance we measure that velocity from. So we'll call that initial radius. Okay. And then also what's going to be important is the angle that's coming in at. So we have some initial angle. That's supposed to be a theta. It didn't come out so good. Theta sum 0, so some initial angle. And I don't quite know how to factor the initial angle in yet. I didn't get that far this morning, but and I still have some questions about this where I read it. The author said, consider a polar version of an ellipse, and or a conic section in general, actually, he said, and he was calling the top number h. I'm not sure why he was using h. And then here, let's let E be h minus 1. So then we would have times the cosine of theta. So one question I haven't resolved yet from reading the paper is, why are we letting E equal h minus 1? And I don't know yet. So E is h minus 1, and I have to look at the references to the paper, because the paper didn't explain it. It just said, hey, let's do this. So then he goes on to talk about what h could be. And based on the idea that one of Newton's law of gravitation, that the force between two objects is inversely proportional to the distance they are apart, and then the product of their masses is in there also. And so h is going to be equal to the initial distance of the object from what it's orbiting times the initial velocity squared. So we got some kinetic energy thing going on there, divided by the universal gravity constant g times the mass of the object we're orbiting. And so E would just be that minus 1. Depending on how fast the object is moving, it's possible that the numerator could be greater than the denominator. If that's the case, then we're going to end up with a hyperbolic orbit, because we got this thing screaming in towards some orbiting body, and that orbiting body is going to cause it to whip and change direction, but it was moving so fast that it's going to escape the gravitational pull. And so we have this, you know, these, what are those called? Asymptotic path on each side there, and we break it. So kind of like the way we try to slingshot satellites around objects out in the solar system, like we slingshot objects around Jupiter trying to get out to Pluto, for example, and leave our solar system. So if we can get it moving fast enough, then we can whip around it. If we slow it down a little bit, then what's going to happen, the numerator will be less than the denominator, in which case we'll get E is a proper fraction, and then it'll get thrown into an orbit around the object. So like when we wanted some of our rovers to circle Jupiter a few times to try and, you know, map out what's going on with all those clouds. So we slowed it down, but then somehow we got to speed it up again to try and zip it out. But that's complicated too, and I don't know enough to get into that whole thing, because I know there's, with orbital mechanics, there's some backwards principles that go on. With respect to the orbit. The closer you are to the object, the faster you will end up moving in orbit. The farther away, the slower your orbit will be. So what that means is when you have a highly eccentric orbit, new page. So here's like the center, the thing we're orbiting about, and say here is the eccentric orbit, perhaps. So one of the foci would be right there. What happens is, because we're farther away over here, the velocity is slower on this side, and when we're in closer, the object is going to be moving faster on that side. Right, yeah, because it has to do with the momentum, yeah. So there's some wild stuff there, more than we have time to get into here. So I just looked up some numbers to try and see if I could calculate what E is for the International Space Station, aside from the numbers I made up here. Online in a variety of places, I found a few things. I found, let's see, G, the gravity constant. Come on, give me a pen. There we go. Is equal to 6.7 times 10 to the negative 11th Newton meter squareds, kilometer squareds. So G has a kind of crazy thing going on there. I also need, if I'm talking about the International Space Station, I need the mass of the Earth. And the mass of the Earth is approximately 5.972 times 10 to the 24th kilograms. So my denominator for H is going to be G times M, and if we multiply G and M, then, oops, I did that wrong, that's in mass of the Earth, I get it's approximately 4 times 10 to the 14th. Now, if I'm going to have something with an elliptical orbit, then I'm hoping that the initial distance and the velocity at that distance squared is going to be less than that. Otherwise, it's not going to be an elliptical orbit. So I want that to be less than 4 times 10 to the 14th. Otherwise, we'll end up with some other kind of orbit. Now, it's possible you can end up with a parabolic orbit or a circular orbit, but those are pretty darn unlikely. To be circular, these two would have to be equal, and to be parabolic, this would have to be double G times M. And the chance of that happening is infinitesimally small. It's like almost impossible. It doesn't happen. Okay, so parabolic and circular orbits are pretty unlikely given the range of possibilities, because they have to have exactly a 0 for eccentricity or exactly a 1. Things don't work out that nice. So then I looked up what? I looked up the average speed of the International Space Station. So V average of the International Space Station is 28,000 kilometers per hour, according to one site. Now I only checked that in one spot, so I gotta look it up somewhere else. So I think that's okay. And then let's see what else. I know, for example, that the closest it is approximately, so R0 is approximately 6,760 kilometers. The furthest it is roughly 6,860 kilometers from the center of mass of the Earth. So then if I multiply that stuff together, I get a numerator of R0, I'm going to call that V0 squared, and that ends up being approximately 5.3 times 10 to the 12th. And so I got my wish. That product is smaller than my denominator, which is what I need to get that eccentric orbit. And so this is where I ran out of time. So I haven't quite figured out what H is yet. So H is going to be the ratio of these guys -1. So I'm just going to plug that into Google and see what we get. And I'm curious to how it compares with the E from the previous calculation. So H is 5.3-ish times 10 raised to the 12th divided by 4 divided by 10 raised to the 14th. So H is pretty little, 1.59-ish times 10 to the negative 12th. Wait a minute, that doesn't look right. Did I type something wrong? No, I think I typed that right. Parentheses just to double check. Oops, and put a multiplication in there. Now I get the same number. Okay, so that's H, and then I want to go that -1. And so, oh, really? Oh, is that right? Oh, that gives me a highly elliptical orbit. That can't be right. Wow. H -1. That doesn't look right. Let me write something else down here. So 5.3 times 10 to the 12th divided by 4 times 10 to the 14th. That's going to be 5.3 over 4, which is a little bigger than 1, times 10 to the negative 2, right? So let's get rid of all this. Oh, I see. I mistyped that right there. Aha. So it's going to be 5. I way miscalculated that. You guys need to yell at me when I do that stuff. 5 divided by 4 times 10 to the negative 2. And I can't type again today. There we go. Okay, so that's our H right there. Is that what you got? Okay, so that other crazy number I got was nonsense. And then if I do 1 minus that, or that -1, that's still, ooh, I got a -2. That's okay. I did see there was an absolute value in there, but that's highly eccentric, not circular. So my velocity, there's something wrong with my velocity. Huh. Okay, I'll have to do some more research on it and get back to you later. That was average velocity, yeah. But since it's not a very elliptical orbit, it shouldn't deviate too much, I think. But I don't know. Yeah, I got to get some more details about that orbit of the International Space Station, because it shouldn't be that can't be right. Because if I graph this in Desmos, wouldn't you have to have what, Clint? It's got to be the speed at the given radius. Yeah. Yeah. So. It's moving the fastest, yeah. But but the average radius is still pretty close to that, so it shouldn't, yeah, that shouldn't matter too much, but I guess it is. What did we get for h again? 0.1 what? Anybody write that down? 1325, okay. And then divided by, what do they have? 1 plus h minus 1, and they said take the absolute value of that actually. So 0.986, what? 675, and then times the cosine of the angle theta. And we get that very elliptical, that, yeah, very eccentric, excuse me. Yeah, that can't be right. Okay, so something's wrong in my calculation. All right, so back to the drawing board. I need to do some more research. Oh well. All right, we got time to do a different problem. Let's see, what should we take a look at? How about, let's take a look at that sample test. Yeah, so section 6 is mostly about kind of just playing around with the parameters of a polar conic section, given a little information about the ellipse or whatever it is, trying to come up with an equation for it is mostly what the homework's like. And I think you guys won't have much problem with it. It's mostly messing around with algebra. Oh, by the way, a useful site I find for playing with conic sections is Wikipedia's conic section page. Conic sections. Wikipedia. Sections with geometry, that's just kind of wild. I think that needs to be a poster in my bedroom. But what they have that I really like down here, they talk about the eccentricity very well. They have this nice chart relating the equation, the eccentricity, C, the linear eccentricity, which is also that half the distance between the foci, the latus rectum, which is a vertical cut through one of the foci, and then the location of the focal parameter here is the distance from the focus to the directrix, is what that represents right there. So they have all these nice formulas and how everything's related. And they have some good graphics to go with them there. So, so where does it start? Yeah, so conic parameters section of this page is like a summary of everything you need to know about conic sections, and it gives you information about how to relate the rectangular to the polar. And let's see, I had made a note about that. Yeah, and it's, yeah, so it's, yeah, it's the one that's closest, like for an ellipse there. Oh, the plural of directrix, directrices. Excellent. Okay, so now I know. So let's see, there was one, what is this, 9, I'm here, 6. So there was one thing I thought they should have on here that I don't think they do. Oh, come on, where are my notes? No. Oh, next section. Here we go. No. Come on. There we are. Let's see, do they show it here? Yeah, okay, there we go. In our book, they called the numerator of the polar version K. Here they call it L, and that's that latus rectum, which is the vertical distance through one of the foci through the major axis, so that length right there. So that's the numerator in polar, and it turns out that's E times P. E is the eccentricity, P is the distance from the focus to the directrix. So there's just a couple of ways to think about it, which is kind of nice. And then they give you ways to relate A, B, and C to those other things here. Okay. enough with conics for now. Let's see, somewhere in here I have a sample test, and this one right here. Okay, so yeah, I'll supply polar paper for the test, and yours will be similar to this, but it won't be multiple choice. You'll have to draw stuff for me. Like this is like this equation right here. Instead of just rewriting it in polar, I'm going to ask you to graph it and rewrite it in Cartesian. And that will help confirm what the graph is. So does anybody remember what this graph is going to be right here? What's that? It's going to be a circle. And the it's going to be kind of centered on the x-axis. And this number out front is the diameter of that circle. So the radius would be 1 for this guy right here. And if you graphed it in polar, you'd see that. And then we can convert to Cartesian. So let's just take a quick look at that one. And I'll also on the test be pretty clear. This is the polar section, do polar stuff. This is the parametric section, do parametric stuff. So you gotta do some mind shifts during the test. So r equals 2 cosine of theta. Before I graph it polar-wise, I just want to think about it rectangular for a moment. And our connection between rectangular and polar is this triangle right here. And so according to this triangle right here, Pythagorean theorem tells me that r squared is equal to x squared plus y squared. And that if the cosine will be x over r, so x is equal to r cosine of theta. Y is equal to r sine of theta. And then y over x is equal to the tangent of theta. So those are some useful things when I'm playing around. So if I wanted to think about this thing in rectangular, I need to get rid of r and the cosine. So first I'm going to do with the cosine here. And cosine would be x over r. So then on the right side here, I could say I have 2 times, x over r equals r. And the reason I'm doing this is because I was thinking, oh, I can put that r to the other side and get an r squared. So I don't have to worry about square roots. So r squared is equal to 2x. And I know r squared is equal to x squared plus y squared. And then looking at that, you might say, hey, that doesn't look like the equation of a circle. But it is an equation of a circle hidden. So if I bring the 2x to the left side, I'll have a minus 2x, I'll have a plus y squared, and I'll have equals 0 on the other side. We can complete the square on this part right here. So to complete the square, remember you take half the middle term, that would be -1, and then you square it. -1 squared is a +1. The whole point of that right there is now this is a perfect square. This whole part right here is the square of x minus 1. Now I can't just add 1 on the left, I also have to add 1 on the right. So I'd have to put a 0 plus 1 on the other side. Now I can say, oh yeah, this is a circle. What's the center of this circle? 1, 0, yep. And what's the radius? Yeah, radius is 1. And I mentioned earlier that that 2 right there is the diameter of the circle when I graph it. So then a question on the test would be, can you convert this into a rectangular equation? This is a rectangular equation. You could stop there totally. I usually like to take it a little farther to confirm the center and the radius that I believe from the polar version. Does anybody remember the period of this guy right here? When we graphed it before? It ended up being pi. Yeah, the whole thing got graphed in pi. Now in rectangular, the period of sine and cosine is 2 pi all the time. But in polar, it depends. It's never, it's just weird. Okay, so for example, some other things to consider, we looked at the function r equals cosine of 2 theta. That was not a circle. What was that? It was a flower or a rose. And do you remember about the petals? It had 4, yeah. So this is a 4-petaled rose or flower. And does anybody recall the period of that sucker? It was 2 pi, yeah, period was 2 pi. Compare that with the 3-petaled rose, cosine, or it could be sine, it just is a rotation of 3 theta. That's a 3-petal. Period, anybody recall? Yeah, period ended up being pi on that sucker. Yeah, so weird stuff happens with these guys. And you can have fractional numbers in there, then you get these crazy interlocking leaves when you do that. And then, let's see, what else did I want to mention about these guys? Oh, yeah, the idea of rotations. So I just want to demonstrate rotations. And let's see, do I have a new, okay, you were a failure, you can go away. Oh no, we'll use you. Okay, so, oh, that's another interesting thing here. The focus isn't at the origin. Oh, okay. I'll dig into this more, see if I figure it out later. Anyway, but check this out. Nah, you're going away. You suck. Sorry I messed that up. I thought. Oh well, it just goes to show that I mentioned this before, the majority of math I've done in my life was wrong the first time I did it. So given that I teach math, I get to do math right a lot, but I still believe that in my lifetime, at least half the math I've done was wrong. Yeah, so I don't know how it is. That's sad, isn't it? Oh my God, that's depressing. No, it's not. I don't mind. It's the, you know, the thrill of it's an adventure. What's that? Yeah, yeah. Let's take, I don't know, let's put a 3 in the top and a 0.5 in the bottom. Oops, 5, what is that? Oh gosh, 5. Hello, where are you? Oh, I zoomed in too far probably. There we go. Okay, so there's an ellipse. Let's make it more eccentric. Let's make that a 0.7. Ah, there we go. And then I'm going to make a slider with a -a slider. And so what happens is, I mentioned this earlier, polar is great for rotating stuff. What is this thing rotating about? The origin or the pole. And what's special about, for this equation, what's special about the origin of the pole? It's the focus of this ellipse. Yeah, so we have a fixed focus there and we're rotating about that fixed focus. Okay, so it's easy to change rotational perspective with polar. If I wanted to shift it left and right, I would want to be in rectangular coordinates, not polar. Okay. So similar, let's get rid of some stuff here. So there's my circle, and if I rotate it, that would be kind of like the 3 times the sine there. Or if we go in here and multiply this whole thing by something, we could have a flower, for example. Ooh, oh, it's bigger, right? No, where'd you go? Oh, you want a times, I bet. Aha, there you go. Picky computers. And then we can rotate the flower, which is kind of fun. Wee-hoo. Okay, so some other things to review in our last couple of minutes. Important formulas. Does anybody remember polar area? It comes from the idea of a sector of a circle. So it turns out all we did need is a little ratio and proportion to figure it out. And what we end up is the integral of 1/2 the radius function squared d theta gives us our polar area. We just have to decide what the bounds of that integration have to be. And polar area isn't nearly as tricky as parametric area, because with parametric, the thing can loop back on itself in weirder ways than polar. Okay, polar is usually not too much of a problem. The r squared takes care of negatives, which is kind of nice. So polar area is pretty sweet. How about polar arc length? Since it's arc length, we got the Pythagorean theorem involved. And although at first it looked kind of complicated because there's a dx d theta and a dy d theta in there, it cleaned up pretty nice to be r squared plus dr d theta squared with respect to theta. And like problems with arc and rectangular coordinates, this square root often makes it unsolvable. There is no answer. So for example, we haven't done too much with arc length, although I mentioned it. It's because for most functions, you cannot find an antiderivative for that sucker. So area in polar isn't too bad. We did the area of an ellipse with polar. We did the area of an ellipse with parametric. But once you try to do arc length, you get nothing. And it turns out, actually, when you mess around with ellipses, whether you're in polar, rectangular, or parametric, the arc length of ellipses leads to a whole new class of function called elliptic integrals. And so if you were trying to find, and this happens even with some normal cycloids, yeah, actually you can pull off an arc length. We did that in class one day. But if you try to do, remember the bicycle reflector problem? If you try to find the arc length of that, can't do it. You get what's called an elliptic integral, because it's kind of related to an ellipse. And if you plug it into a computer algebra system, they'll say the answer has something to do with E of blah, 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 where E is the elliptic integral function, which you can only compute numerically because there are no antiderivatives for it, which is kind of wild. So it's a whole new class of function. Couple more formulas, and then I'll shut up. Parametric wise, things aren't too bad. Parametric. As far as areas go in parametric, essentially we have a substitution that goes in on that, and so it gets a little more complicated. The area has to be an absolute value, and we'll have the integral of y times x prime, or I guess I should say dx dt. Let's change that. Dx dt dt. And if before we had problems when, if the function went negative, when we were looking at total area, we had to deal with absolute value. Now we have to consider, well, what if dx dt goes negative? That's a problem too. That means if dx dt is less than 0, i.e. negative, then that means the curve is looping back on itself. So that would be this section right here, in which we have some weird stuff going on with areas, and we played around with that a little bit one day. Other formula that's important is parametric arc length, and that one's not bad at all, except we got that crazy square root that often messes it up. That's just dx dt squared plus dy dt squared inside there. Other interesting thing parametrically was the idea of speed. Anybody remember what speed ended up being with parametric stuff? So we have x velocity, we have y velocity. If we put them together, we get speed. How do we put them together? It's not slope. What is it? Yeah, it's Pythagorean theorem. It's basically the inside of the arc length. So speed is just the square root of your dx dt plus your dy dt. Now notice I'm calling it speed, not velocity, because I lose track of the direction because I have the square root of squares, so we lose direction there. So that's another useful one there. All right, that's it for now. And we'll take a test tomorrow. So the test will be probably half the length of that sample test I put up here. The sample test had 13 questions. I'm going to whittle it down to 7-ish questions. You'll have to do at least one graph of a polar, at least one graph. You have to do one graph of a polar, one graph of a parametric. You do a little bit of calculus on each, and then you'll play around with a couple of probably an ellipse problem. All right, go forth and do good things today.